Okay, continuing with example 10. So we have isosceles right triangles where the base is a leg. So if this is S, and the area is really simple. Area is 1/2 S times S. So the volume would be 1/2. I notice I just put that up front. You could put it on the inside or you could put it on the outside, doesn't matter. S squared, 2 plus x minus x squared, quantity squared, dx. All right, we have isosceles right triangles where the hypotenuse is the base this time. Okay, so this time this is S. So remember this is 45 degrees here. If I cut that in half, okay, that's S over 2 and that's S over 2. So the area would be given by 1/2 base times the height, which would be 1/4 S squared. So then the volume be 1/4 the integral from -1 to 2 S squared dx. Okay, and lastly we have an equilateral triangle. Hopefully you remember your equilateral triangle stuff. We know this is 60 degrees, this would be 30 degrees. If the whole thing is S, this is S over 2. So this is S over 2 times the square root of 3. So the area then is 1/2 times the base times the height, which is square root of 3 over 2 times S. So we get square root of 3 over 4 S squared. Okay, so the volume is given by square root of 3 over 4 integral -1 to 2. And now that I'm thinking about it, it might not hurt just to do this S squared dx. That way you don't forget to put the squared like I almost did a couple of times. So there we go. This is when we have nicely, we can figure out the area just by using geometry, and that helps us to get the volume. Okay, this time we're going to figure out the area a little bit differently. All right, so we have, this is a calculator problem, so it'd probably be good to put these in your calculator. This is going to be my f of x function right here. This is going to be my g of x function. We're going to need to figure out where f of x equals g of x. Okay, use your calculator for that and label it so we can use those values later. I think that this is what it is. Okay, so we have that A and B value. Okay, so an oil spill on the surface of the water has that shape and it's given by region R there. So the depth of the oil spill is measured perpendicular to the x-axis. So it's kind of like we have this shape on the top of the water. And to find the area, we're going to do this times our depth, whatever that is. The depth is given by this equation. All right, so we're doing this, top minus bottom, that f of x minus g of x times whatever this is, the depth. Okay, so the area is given by our slice f of x minus g of x times the depth. Okay, because it's f of x minus g of x. So that gives us an idea for the volume. Since I already wrote this, I can use it from A to B. I have f of x minus g of x, that quantity multiplied by d of x dx. And this is a calculator problem, so you simply type it in. 4.435 would be our volume, units cubed. Okay, and last one, y equals 5x. Y equals -1/5 x plus 3. I guess I don't need all of this down here. The base, that's the base of the solid. Oh, and y equals 0, so I'll put that on there. And we're talking about slices that are perpendicular to the y-axis. So I'm going to draw that on there. Okay, so I know that that's a differential of y. I do need to figure out what this y value is at the top there. So to do that, I'm going to set these equal to each other. 5 plus a fifth is 26 fifths. And so x equals 15 over 26. But I need the y value because it says here, this is a clue, a of y. I drew my picture, dy. So if I plug it into this one, 5 times that, our y value right there, that would be 75 over 26. All right, so the volume, and we're going from a y value of 0 to y value of 75 over 26. Our area was given to us. That was nice. So the volume is, take the antiderivative. That would just be y from 0 to 75 over 26. Okay, so since I don't have a calculator handy, I'm just going to write it like this. Minus 0, and there we go. So that wasn't so bad, and that concludes section 6.3.